Welcome everyone. For today's prep, we're going to start to look at another series test, and this one's called the direct comparison test. And the idea behind this test is, well, first let's read through it, and then we'll mention when we use this test. All right, so let's first read through the statement here. Suppose we have a series sigma an and another series sigma bn, and these are series that all have positive terms. So if we look at just our infinite lists, all the terms in those lists are positive, and then when we do the series, we're trying to add all those terms together. So everything here is positive. Well, what does this comparison test say? So if the series sigma bn is convergent, and all of the terms an and bn satisfy this inequality, so an is less than or equal to bn for all n, then series sigma an also has to be convergent. And it goes the other way as well. So if sigma bn is divergent and bn is less than or equal to an for all of the terms in our lists, then sigma an has to diverge as well. And you can kind of see why. So if we try to add up all the terms, well, then the sum should satisfy that inequality, but then this is going to be infinite, so that's going to make the series sigma an infinite as well. Just like if we back up here, if we try to add up all the terms, if this is finite, well, then this has to be finite as well. It can't add up to infinity. All right, so how do we actually perform this test? So why is it called the comparison test? Well, sigma bn, we call this our comparable series. So this is the series that we actually know what's happening. So in order to use this test, we have to know what's going on with at least one of our series here. So usually in the way we do this, sigma bn is called our comparable series. So that's our first step, is to figure out what the comparable series actually is, and then explain why it's convergent or why it's divergent. All right, so that's the first step. So sigma bn is our comparable, and then sigma an is the series that we're actually testing. All right, so once we've figured out the convergence of our comparable series, then the next step is to state the necessary conditions. Now, as we've seen, like with integral test, sometimes there's quite a few conditions that have to all be satisfied. In this case, there's only one. The terms have to be positive. So you just want to check this. Sometimes you have to check it, but usually this is just a statement. So you state the necessary condition. And then the third step is we have to actually prove this inequality. So this is our next portion. We got to deal with that inequality. And this is where we do a little bit of work. We actually have to prove it. And then once we've proved it, then we basically have all the info that we need, and we can do our conclusion. So this is how a usual comparison test is going to work. So again, in this statement, sigma bn, this is going to be called our comparable series. And usually, this is a p-series or a geometric. Usually. So the idea behind when we actually use this test is that we use this test when our series kind of looks like a p-series or looks like a geometric series, but isn't exactly a p-series or geometric. All right, so let's try an example. See how this works. And maybe we'll come back and talk about the starting index value again. And just for help, again, we use this test when our series kind of looks like a geometric or a p-series. So we're going to be falling back on these usual things that we've looked at. When is a geometric series convergent? When is a p-series convergent? So let's try an example. So we've got this unknown, we've got this series, sigma n equals 1 to infinity, 1 over 3 to the n plus 1. So this portion looks like an exponential, so we're kind of thinking geometric, but this plus 1 makes it not geometric. So it's not really a geometric series here, but it's kind of close. So we're going to compare it with a geometric series. All right, so the first step is we've got to figure out we've got to get our comparable series. So we have to figure out what we're going to compare this to. And when we do that, we're going to call our comparable series sigma bn, and for short, maybe it'll come up, we'll call the series that we're testing sigma an. All right, so how do we figure out what series we're going to compare this to? Well, we use the dominant terms that show up in our fraction. So we pick out the dominant term in the numerator, which, well, there's only one, so it's going to be 1. And then we pick out the dominant term in the denominator. So as n gets really big, which term kind of takes over the show? And that's going to be this exponential term. So that's the one that takes over. So we're just going to use those. So our comparable series here is going to be the series sum from n equals 1 to infinity, and it's just going to be the 1 over 3 to the n. And with a little bit of rewriting here, we can a little bit more easily recognize that this is indeed a geometric series. So if we kind of factor off that common exponent, we can write this as 1 over 3 all raised to the n. And now we see what the r value is for our geometric. So once we've figured out our comparable series, we want to explain if it's convergent or divergent. That's kind of the important thing here. So what do we see here? Well, it's convergent. And let's go through our usual explanation. So this is going to be a convergent geometric series Let's state the r value. So the r value in this case is 1 over 3. And then let's state the necessary inequality. So the absolute value of r has to be less than 1 for a convergent geometric series. Okay, so great. We have our comparable series, and now we have to do a little bit of work. So step 2 is we just have to check, in this case, really just state the necessary condition. So an is 1 over 3 to the n plus 1, and bn, 1 over 3 to the n, are all positive. These are all positive numbers. So we only have positive numbers in our list. So everything is positive here, everything is positive here, and we're doing addition, so it just keeps it positive. So these are all positive terms. So we do have to state that. Okay, so now we're ready to prove the inequality. So what do we have? Which inequality are we going to do? Well, we suspect that sigma bn, well, we know sigma bn is convergent, so we're suspecting that sigma an is going to be convergent. So if we go back up to the statement of the test, let's just pop back up there. Which inequality, which version are we going to prove? Well, since we're suspecting, well, we know sigma bn is convergent, we want to prove this inequality, that an is less than or equal to bn. If we had found that sigma bn was divergent, then we'd prove the other one. But in this case, we want to prove an is less than or equal to bn. So how do you prove an inequality? Well, basically, you start with what you want to prove, and you simplify it until you get down to something that's obviously true. So let's start with, first, by just filling in what we know an and bn actually are. And I'm using this logical equivalence, if and only if. It's kind of like the equal sign for logical statements. All right, so if we fill in an, then this is what we're trying to prove. So we need to know, is this actually true? Well, maybe it's not so obvious. So let's actually cross multiply. So if we cross multiply here, the 3n is going to end up over here, and then the 3n plus 1 is going to end up on the other side. So we're going to end up with 3n is less than or equal to 3 raised to the n plus 1. And at this point, I would consider this obviously true, because what do we have? We've got some number, and then on the other side of the inequality, we've got the exact same number, but then we're adding on 1. So that's obviously true. When you have the same number on both sides, but then you're adding a little bit extra, yeah, that adding a little bit extra is going to make it bigger. But if you really want to be thorough, you can go a little further here. And if you subtract 3 raised to the n from both sides, then you can get it then you can get something that's, well, hopefully definitely true. 0 is less than or equal to 1. There's no dispute in that. So if you subtract 3 raised to the n from both sides, then you can get it down to this. So since this is true, well then, by this logical equivalence, this statement must be true, which means this one must be true, which proves the inequality that we wanted. So I'll say here is a perfectly fine stopping point. So this proves it. So that's the kind of one way to prove an inequality. Start with what you want, and then simplify it until you get down to something that's obviously true. And then once you've done this, the last step, conclusion. So what's our conclusion here? Well, since we went through, we found our comparable series, we stated the necessary condition, we proved the inequality. Now, since sigma bn was convergent, sigma an has to converge as well. And let's state what test we used. So for an abbreviation, we'll call this is the direct comparison test, so I'll abbreviate it DCT. And notice that I named this sigma an just so I didn't have to rewrite this again. If I didn't name it here, then you'd actually just want to rewrite the original series here. All right, so let's try one more example using this approach. So we've got the sum, sigma n equals 1 to infinity, 3 over 2n squared plus 2n squared plus 5n plus 1. And, well, this isn't really a p-series. It's not really a geometric series, but it kind of looks like a p-series. We've got this n raised to a power here. All right, so first step, we want to get our comparable series. What are we actually going to compare this to? And again, the way we do this is with dominant terms. So you look for the kind of the term that takes over in the numerator, which is the 3, and the term that takes over in the denominator, so the 2n squared. So we'll call our comparable series here sigma bn, and we'll call our original one sigma an. And for sigma bn, it's going to be the sum from n equals 1 to infinity, 3 over 2n squared. And if we factor out the 3 and the 2, we end up with the sum of 1 over n squared, n equals 1 to infinity. And this portion, this is a p-series. So the multiplication by 3/2, that's not going to change the convergence one way or the other. So what we have here is a convergent p-series with p equal to 2, and again, state the necessary, kind of our usual routine for these geometric and p-series. So this is a good explanation. So the p-value has to be greater than 1 for a p-series to be convergent. All right, so once we have our series, our comparable series all figured out, now we're ready for the necessary condition. And in this case, sigma an and sigma bn all have to be positive. Or not sigma an, just the individual terms in our list. So an, which is 3 over 2n squared plus 5n plus 1. And bn, which is 3 over 2n squared. Everything here is positive. So all positive stuff here. Remember, n is going from 1 to infinity, so there's no negative n values. So this is all positive, this is all positive. So we're good. All right, so we've done our necessary condition. Now we're ready for our inequality. And what inequality are we going to prove? Well, again, sigma bn is convergent, so we're suspecting sigma an is going to converge as well. So in order for convergence, we want to prove that an is less than or equal to bn. Because what happens then is, if we were to add up all the terms, then the sum of an must be less than or equal to the sum of bn. And if this one's finite, then this one has to be finite as well. All right, so we want to prove this. So let's start by filling in what our terms are. So an is 3 over 2n squared plus 5n plus 1. That's going to be less than or equal to 3 over 2n squared. Again, not so obvious at this point. So let's cross multiply. And let's take the 2n squared, we'll multiply it over here, and then we'll take this whole thing and we'll multiply it over here. So what do we get? Well, we get 3 times 2n squared over on the left, and then on the right-hand side, we get 3 times 2n squared plus 5n plus 1. And maybe I should have multiplied that out. Probably. Oh well. Let's multiply it out now. So we get 6n squared less than or equal to 6n squared plus 5n plus 1, or plus 15n plus 3, rather, if we distribute the 3. And again, we run into the same kind of scenario here, that we have the same number showing up on both sides, but then we're adding on some additional stuff over here, some additional positive terms. So whenever you get to something like this, where you have the same number on both sides, but then this side has some additional stuff, well, that's going to be the additional stuff, as long as that stuff is positive, which in this case it is. So this is true. And if you wanted to, you could go one step further, subtract the 6n squared off, and then you would definitely have something that's true. 0 is definitely less than 15n plus 3. All right, so that proves it. We got to an obviously true statement. So then finally, conclusion time. And we can say that sigma AN converges. And then we just want to state which test we used. So we use the direct comparison test. All right. So we're going to be seeing another comparison test in class called the limit comparison test. So it'll be similar. So we'll see you then. Bye-bye.